Hi, welcome to lesson 4.2, where we're going to learn about mathematical expectation for bivariate distributions and the correlation coefficient. So mathematical expectation for bivariate distributions is defined in a way that's very similar to the way we did in univariate distributions. Suppose that x and y are two discrete random variables with a joint PMF, f of x and y. If u is some function of x and y, then we can calculate the expected value of u by summing over all of the xy combinations in the sample space, the function u evaluated at those values of x and y, and multiplied by the PMF evaluated at xy, and then just add them all up. We're going to talk about some special expectations. The first one is the mean. If our function of x and y, u, is equal to x, then we call the expected value of x the mean of x, and we give it the notation mu with a subscript x, so we know that it's the mean of the x random variable. And similarly, if we have our function u equal to y, then we can also talk about the mean of y. Let's look at an example. This is problem 4.2-6 from Hogue, Tanis, and Zimmerman. We have the probability mass function, little f of xy, equal to 1/6. For values of x plus y that are greater than or equal to 0 and less than or equal to 2, and x and y are non-negative integers. So let's take a look at what our sample space looks like here. Here are the possible combinations of x and y, represented by dots, and the probability of each of them is 1/6. Now, if I want to find the mean of x, I'm going to add up for all of the x, y combinations, x times f of xy. So, start with my first dot. I've got x equal to 0. I've got f of x and y equal to 1/6. And I move on to my next dot. Here I've got x equal to 1. My PMF is 1/6. I move on to my next dot. X is 2 times 1/6. Move on. Here I've got x of 0 times 1/6. X of 1 times 1/6. And x of 0 times 1/6. This gives me a mean, mu sub x, of 4/6, or 2/3. I can do the same thing for all the values of y. I sum up over all the xy combinations in the sample space, y times f of xy, and also get a mean of 2/3. The mean of x and the mean of y are not generally going to always be equal. It just happens that that is the case in this particular problem. The next special expectation we're going to talk about is the variance. This is also defined very similarly to how it was in the univariate distributions. If our function of x and y is equal to x minus the mean of x squared, then we can take the expected value of that and call it our variance of x. And we give it the notation sigma squared with a subscript x. We could also do the same thing with y, take the expected value of y minus the mean of y squared, and that would be our variance of y. So coming back to our example, I'm going to calculate the variance of x, sigma squared sub x. I'm going to use the computational formula that we've used throughout the course. We can take the expected value of x squared minus the mean of x squared. Still works in this situation. I find the expected value of x squared by taking the sum over all of the possible xy combinations in the sample space of x squared times f of xy. Gives me an expected value of x squared equal to 1. And then to find the variance, I subtract my mean squared, and it gives me a variance of x, sigma squared sub x, equal to 5/9. Can do the same process to find the variance of y, and it should also be equal to 5/9. And again, this is because of the nature of this particular problem. In general, the mean of x is not equal to the mean of y, and the variance of x is not equal to the variance of y, except in certain special cases. The next special expectation we're going to talk about is called covariance. Covariance tells us something about how the x and the y values vary together. So we use the notation sigma with a subscript xy, and it is the expected value of x minus the mean of x times y minus the mean of y. Computationally, it's often easier to use a formula that the covariance of x and y is equal to the expected value of x times y minus the mean of x times the mean of y. And that formula is derived in the book. I'm not going to show the derivation here because it is a little time consuming, but I am going to do an example using each of these formulas to calculate the covariance. Coming back to our example, I want to calculate the covariance of x and y. So I'm going to take the expected value of x minus the mean of x times y minus the mean of y. So I start with my first point. My x value is 0. I subtract off the mean of x. My y value is 0. Subtract off the mean of y. The probability that x is 0 and y is 0 is 1/6. And then I move to my next point. X is 1. 1 minus the mean of x is 1 minus 2/3. Y is 0. 0 minus 2/3 multiplied by f of 1, 0, which is 1/6, and so on. Move to the next point and continue until I've finished all of the points in the sample space. And I get a covariance of negative 0.2778. Let's look at how we can use the computational formula. Here I'm going to start by calculating the expected value of x times y. So for each point, I multiply x by y. Notice that only one of these is actually not 0. I get the expected value of x times y of 1/6. I subtract off my mean of x times my mean of y, and I get negative 0.2778. This is the same answer that I got before, kind of showing us that, yes, both formulas do give us the same answer for the covariance. A couple of things to know about the covariance. One thing to note is that the covariance of x and x is equal to the variance of x. Similarly, the covariance of y with y is equal to the variance of y. Also, the covariance of x with y is the same as the covariance of y with x. It doesn't matter which order we look at the variables in. Covariance gives us a measure of sort of how variables relate to each other. If variables have similar behavior, the covariance will tend to be greater than 0. So by similar behavior, what I mean is if x is above average, then y is also above average. And if x is below average, y is also below average. That would be similar behavior. And they would tend to give us expected values where I would be have a positive value in that expected value. If, on the other hand, I tended to be above average for my x value at the same time that I was below average for my y value, then that product in my expected value is going to tend to be negative. So variables with opposite behavior have covariances that are less than 0. The sign of the covariance tells us the tendency in the linear relationship between x and y. But the magnitude of the covariance is very hard to interpret. And the reason it's hard to interpret is because it really depends a lot on the units in which the variables are measured. So we would like to have a way of measuring the strength of the linear relationship between x and y that the magnitude can help us with. So we have another value, which is called the correlation coefficient. and we use the notation rho. Kind of looks like a fancy P, but it is the Greek letter rho for the correlation coefficient. It's defined as the covariance of x and y divided by the standard deviation of x multiplied by the standard deviation of y. And it turns out that this value always takes on values between -1 and 1. Coming back to my example, my correlation, rho, is going to be my covariance divided by my standard deviation of x times my standard deviation of y. And this gives me a correlation of -0.5. Just as the sign of the covariance gave us the tendency in the linear relationship between x and y, the correlation gets its sign from the sign of the covariance, so it still tells us whether we tend to have a positive or negative linear relationship between x and y. But when we're working with correlation, magnitude quantifies the strength of the linear relationship between x and y. So if the absolute value of the correlation coefficient is close to 1, then it means we have a very strong linear relationship between the variables. If the absolute value, the magnitude of the correlation is close to 0, it means we have very weak linear relationship between the two variables. How exactly is the correlation mathematically related to using a line to model the relationship between x and y? If we want to fit a line to model the relationship between x and y, we can consider all the lines in two-dimensional space that pass through the point mu of x and mu of y. And these lines have the form y minus the mean of y equals b times x minus the mean of x. This is because the slope of the line b represents the change in y divided by the change of x, which can be rewritten as y minus the mean of y over x minus the mean of x. And if we rearrange things, we can see that these lines have to have this form. Now, the method of least squares chooses a line that minimizes the expected squared vertical distance between the points in the sample space and the line. We're going to minimize the expected value of y minus the mean of y minus b times x minus the mean of x squared. If we take this quantity that we want to find the expected value of, we can actually do some manipulation and show that quantity is equal to the variance of y minus 2b times the covariance of x and y plus b squared times the variance of x. Then we take the derivative with respect to b, set it equal to 0, and solve for b. And we can find that the slope is equal to the covariance divided by the variance of x. Slope is positive when the covariance is positive. The slope is negative when the covariance is negative. And since the correlation is equal to the covariance of x and y divided by the variance of x times the variance of y, we can rewrite the slope as our correlation times sigma y over sigma x. And we can get our least squares regression line of this form. Y equals the mean of y plus the correlation times sigma y over sigma x times x minus the mean of x. And if we wanted to do this for our particular example, we can plug in all these values and get the equation for the line. Y is equal to 1 minus 0.5x, and we can draw it on our graph. Coming up next, we're going to see a video that talks about conditional distributions, and that will bring us through the end of the week. Have a good day.